In this lesson, we're going to talk about specific forces, and specifically, we're going to talk about the weight force, the normal force, the tension, and friction. Part one of this lesson, we're only going to focus on the weight force. So, it's one page of notes. We're going to look at all aspects of the weight force and talk about how it's applied to a very specific problem where an object is on an inclined surface below. But it is such an important force to understand, and it's in almost all of the problems we do. It's worth taking the time. Okay, we know F equals ma, and we know the acceleration near the surface of the Earth is a constant negative 9.8 meters per second squared. So, the force due to gravity, which is the weight force, or for shortened, just your weight, is mg. And when I solve problems, I don't use W, I don't use F sub G, I cut right to the chase. I just use mg and identify that vector arrow as mg. I'll calculate it and deal with it the best I can. Up front, usually first in the problem, and then go on to see what else is going on in the problem. Now we have a very interesting comparison here between the Earth and the Moon. We see that the Moon does not have the same constant gravitational acceleration near its surface that the Earth does. The Moon has about 1/6 the gravity of the Earth, or 1.67 meters per second squared of acceleration. Well, that means the weight of a 1 kilogram object on the Moon and on Earth is different. So on the Moon, a 1 kilogram object has a weight of 1.67 newtons, and on Earth, that same 1 kilogram object has a weight of 9.8 newtons. Now, technically, forces are vectors, so we will have a direction associated with it, and I have in big, bold red letters here, negative y only. So gravity points straight down. We will always identify it in the negative y direction. The other point to note, of course, in this little comparison we did between the Earth and the Moon, is that 1 kilogram is 1 kilogram, whether it is on the Earth or on the Moon or anywhere in the cosmos. Mass does not change. The only way you can change mass is to literally remove material from the object. Okay, so let's see how to handle gravity, the gravitational force in problems. Well, before we get to this little more complicated case where we're inclining the plane, let's just talk about a box, and gravity is the only force acting on the box. Well, if we have a box, and gravity is the only force acting on the box, then it is in free fall, and there is a force mg straight down. So, if an object is near the surface of the Earth, you are always going to put mg straight down, regardless of what the object is doing, whether it's actually moving in free fall, or whether we put it on a table or a surface and allow it to just sit on the surface. So if an object is just sitting on the surface, that mg does not go away. It is still there, just like if the box were in free fall, even though the box is now not moving. But now we have another force. We have the force that the ground, well, that should be perpendicular. My pen isn't the greatest here. The force normal is the force we say that the ground is exerting, and it is straight up, perpendicular to the surface, and if the box is not moving, then those two forces will cancel each other out, so the net force on the box is 0, and the box just begins to sit there. Well, what happens to gravity as we begin to angle this surface? And that's what we're looking at in the picture here. If we angle the surface, so now we've taken the surface and we've angled it up to some angle theta, that does not change the mg for gravity. Gravity points straight down to the center of the Earth, regardless of what is going on in the problem, whether it's in free fall, whether it's on a flat surface, whether it's on an inclined surface. mg is straight down. All right, well, you can see here that we have a little bit of work to do, things to change when objects are on an inclined surface. The very first thing I want you to do when you have an object, in this case a box on an incline, is to get out your ruler and put a new y-axis parallel to the incline, x-axis, parallel to the incline, and actually label that your x-axis. I want you to get your ruler out and go perpendicular to the incline and call that your new y-axis. I will refer to this throughout the notes as rotating the coordinate system. But again, simply ruler parallel to the incline, your new x-axis, perpendicular to the incline, your new y-axis. The very first force I always put in is gravity straight down. Now, you'll also see we have a little bit of geometry here to look at. If I extend my new positive x-axis down, and I look at the horizontal here, I get a right triangle. That's what the perpendicular here is for, to show the right triangle, and that the angle phi and the angle theta, so we have similar triangles. So theta, which is also this theta in the triangle here, here, and here, phi and the 90 degrees make 180 degrees, so theta and phi are 90 degrees. So that means if I have 90 degrees here, the angle that I've drawn inside here will be theta. You do not need to go through this geometry each and every time you solve incline problems. What I want you to do when you solve incline problems is put mg straight down into the earth. I want you to automatically, don't prove it, don't mention it, just label the angle theta as the angle between the mg vector and your new negative y-axis. Let me repeat that. The angle theta of the incline will always become the angle between your mg vector down and your new negative y-axis. And then what I want you to do is immediately write mg cosine theta and mg sine theta. So get mg sine theta. Now look where mg sine theta points, down the incline. So that's the component of gravity that's actually going to pull this box, slide it down the incline. The mg cosine theta is going to be pushing the box into the ground. So if the box is going to sink into the incline, mg cosine theta would cause it to sink into the incline. In this diagram, I have shown a force normal balancing that mg cosine theta so that it does not sink into the incline. All right, well, the other discussion here is, well, what happens when the box now moves in the direction of mg sine theta? Well, it'll slide down the incline. If there's friction between the box and the incline, and this is just a peek ahead because we're going to look at friction in a couple pages of notes in more detail, but if there were friction between the box and the incline, then we would have a frictional force opposing that mg sine theta force down the incline, and now we would have two competing forces for the motion. We would have mg sine theta, and we would have the force of friction. Notice the force of friction will never ever win out and drag the box up the incline. Okay, so if you put a box on an incline, it will either stick in place, which means the frictional force matches mg sine theta or has the possibility for a larger value, and we'll talk more about that in a moment. But of course, friction will not drag it up the incline. The other point that I want to note here is that the total force that the ground is exerting on the box, because sometimes students will kind of miss this. We think of the forces all individually, but then don't think of putting them back together. The normal force and friction together both comprise the ground acting on the box. So the net force that the ground exerts on the box is actually that diagonal here. So some questions will ask you to identify what the ground is doing. Well, the ground does both friction and the normal force in general. If there's no friction, obviously that red arrow would be 0, and then the ground force would just be the normal force. And my last point on this page is to look at mg sine theta and think about what is going on when the box moves down the incline. Remember when we talked about the box in free fall, we talked about only mg acting on the box and it's falling down, and the acceleration due to gravity is g. Well, now for a box sliding down an incline, if I put the g and the sine theta together, and now let's take friction back out of our problem, so pretend there's no friction in the problem, then the box will slide down the incline not with an acceleration 9.8, right? But a smaller value based on g sine theta, and some textbooks will actually label this bracketed term as g effective, E. Hold on, right above it doesn't seem to want to write there. G effective. Okay. The pen is no good there. So if you look at g sine theta itself will go between 0 and 1, so that means the bracketed term goes between 0 and 9.8, so that my g effective will be 9.8 max, 0 min, and if you're a skier, you should recognize what's going on here. When theta is very small, you're on those bunny slopes, the beginner slopes, and when theta is small, g effective is going to be small. As theta approaches 90 degrees, you go to closer to 9.8, and then you're closer to those very steep theta slopes where you have to be a more expert skater. So it was a lot here on this page, I realize that, but I think the discussion was worth it, and we're going to continue on looking at the specific forces, and in our next lesson we're going to learn about the normal force.